afternoon all. Let's start. So I welcome you all to this Institute Colloquium. I'm happy to introduce today's speaker, Professor Axel Kleidon. He comes from Max-Planck-Institute of Biogeochemistry. He did his PhD in metrology in 1988 from University of Hamburg. Then he moved to Stanford for a postdoctoral stint. Then he joined University of Maryland. After spending some time, he joined Biospheric and Theory and Modeling Group of Max Planck, and he has been acting as a professor there. He has published more than 100 research papers in reputed journals and authored several books. One of his recent books is actually on thermodynamic foundation of the Earth system, and he is in process of writing another book which will be coming in the next year that talks about energy, a very short introduction. So he's also a co-founder and co-chief editor of one of the AGU journal, which is Earth System Dynamics. So he is one of the best person if you want to hear application of thermodynamics into Earth system process, land-atmosphere interaction, how the global climate change influences the Earth system process. So it's better to hear from him more. With this brief introduction, I welcome Professor Kleidon.
Yes, thank you very much for coming, and I'm very happy to be here, and I'm very thankful for the hospitality that I've seen here in the last few days. While having a workshop or like a lecture series on that topic. And so what I want to do here today is to give you a few flavors of such a thermodynamic Earth system perspective. And so I want to start first by just raising a few questions that motivated developing this perspective over the last 10 or 20 years. Actually, when I started, you can ask very general questions about, why do things happen and why do processes go in the direction that they proceed? And are there any general operating principles for the whole planet? And when you think and talk to people and so on, then you sooner or later get in contact with the second law of thermodynamics. And I studied physics, and then I switched to meteorology. And in meteorology, you don't hear much about the second law of thermodynamics. So you wondered, well, how does it actually apply to the climate system? And what we have now found out over the last probably 5 or 10 years or so is actually that one can use such a thermodynamic approach to create very simple models of climate and climate change, and to make estimates of climate change that are really derived from first principles and that compare very well with much more complex climate models. And I think this is actually a very nice complement. It doesn't contradict, but it supports them, and it allows for a much simpler insight on what the main processes are that shape or that will shape some of the changes in climate in the years to come with global warming. Another aspect, and this is actually what really drove me into the quest of entropy in thermodynamics, is the question of what is the role of life in the planetary system? Does it regulate the planetary environment? There's especially one hypothesis called the Gaia hypothesis that states that life evolved and regulates the Earth's environment to optimize its own benefit. And when you talk to an ecologist or biologist, they typically think that you smoked too much pot or something when you think about these things. But and this hypothesis was created by a British chemist and inventor, Jim Lovelock. He's now 100 years old this year. And he was motivated to formulate this hypothesis based on thermodynamics, and actually based on non-equilibrium thermodynamics. So it's not quite so far-fetched. And last but not least, we can ask about the role of humans in the Earth system. notice global warming more and more these days. So we know that our combustion of fossil fuels changes the atmospheric composition, changes the strength of the greenhouse effect. And so we clearly affect the planetary environment. And so we can ask, what's more generally, what is actually our role? And we can also ask how is the future probably going to look like? And what I'm trying to show here now with a few bits of thermodynamic bits in an Earth system context is that it actually can provide a basis for giving some of the answers to these questions. Now, thermodynamics of the Earth system is, of course, not new. When you think of different disciplines that together form the Earth system, then you have like pockets of thermodynamics in each of these disciplines. So within atmospheric science, you have atmospheric thermodynamics, where you deal with adiabatic changes, for instance, or adiabatic conditions as parcels of air rise. Or you have geochemistry, which has, of course, thermodynamics involved in it as well, in the lithosphere, or in water, aqueous geochemistry. Also in the biosphere, when you think of life, you have bioenergetics, chemical transformations, and we actually also heard on Thursday morning a lecture by your director on the thermodynamics of protein folding. So there's obviously a lot of thermodynamics in the biosphere, but of course, there's also more. There's ecology and biodiversity and all this stuff. And last but not least, when you look at the humans, we of course also have applications of thermodynamics, for example, in terms of air conditioning or heat engines, car engines, power plants, and so on. But as I show you here, they're sort of like subunits of these different spheres. Now, what I want to get at is actually to apply thermodynamics to the whole planet, right? So actually to say that all of these disciplines are actually really thermodynamic systems and transform, and actually what links them is that they transform energy. And they transform energy in specific ways because it relates to entropy. And so we need to have a good understanding of where entropy comes in and how it actually is represented in these different processes. And what I noticed over the past, actually what's most missing in the understanding of how thermodynamics applies to the planet is actually that radiation also has an entropy. It's something where you can even talk to meteorologists and they don't know. But it's actually something that is very well established, and it's actually ingrained in the derivations of Max Planck when he derived the quantum or the statistical physics of radiation in the beginning of the 20th century. So this is one aspect that we need to know. We need to actually have a broader view of thermodynamics where we also include radiation, where we also include other forms of energy to link these spheres together. And then we can ask about what we can actually learn from this approach. And actually, this is quite a rich approach. On the one hand side, you can ask these quite fundamental questions, but it can also lead to quite applied insights. I'm actually also working on limits to wind energy as a renewable energy source. And that's energy that's generated by the Earth system subject to thermodynamic constraints. And so one can actually also get estimates for how much renewable energy the planet generates, and that can in principle be used, and what the impacts are when you use these forms of renewable energy. And so a starting point to develop such a thermodynamic perspective is to think of different processes in terms of the energy they convert. So I show here a few examples. So up here on the left is a hurricane. And what a hurricane does is it converts latent heat in terms of vapor. When it condenses, it releases heat, so thermal energy, and it's being converted in kinetic energy of the motion that is associated with a hurricane. Here on the right is a plant leaf, which converts sunlight, so it's electromagnetic energy in form of radiation, into chemical energy that is stored in carbohydrates. A power plant, that's probably a quite straightforward example, converts some fuel, for example, brown coal or nuclear energy into heat, and then heat is further converted into electrical energy that is then fed into the grid and exported. And last but not least, also wind turbines, so renewable energy, are energy converters. Each turbine takes kinetic energy out of the atmosphere, converts some of it into electrical energy to also supply us with energy. So these are just examples, but we can think of the whole Earth system as being a series of energy conversions. So we have conversions. I mean, here are the different associated forms. Here I show the connection between some processes, and which, together we call it sort of an onion, because it's like different layers that are being converted. So, we have radiation coming in from the sun, and then it's converted into heat when it's being absorbed. Heating differences can cause motion. Motion is associated with kinetic energy. Then with motion, you can perform hydrologic cycling. You can move moisture up so it condenses, and so it can supply, or it can lead to hydrologic cycling that has different forms of potential energy. It has some chemical energy because the water vapor is basically desalinated water, and it actually also creates some kinetic energy, for example, in river flow when after precipitation arrives on land. And then the water that's on land can actually perform weathering reactions and can drive geochemical cycling. And so we have a chain of energy conversions from radiation down to chemical energy. On the other hand, we have effects, we have alterations. So heat transport in the atmosphere, for example, alters the radiative fluxes that leave the planet. So we have effects here that we need to account, and what I will show you is that actually these effects of those processes are really quite substantial, because they actually affect the limits, the thermodynamic limits that are being set to these conversions. We also have here, I mean, I don't want to go too much into detail. In the interior, you also have basically those conversion processes, but then you also have biotic activity. And biotic activity is somewhat different because it doesn't draw its energy from motion or from hydrologic cycling. It actually draws the energy directly from sunlight. And so it skips these conversion processes and directly takes up solar radiation. And then last but not least, here in the middle I put the humans, because we draw our energy from biotic activity. This is what gives us the calories and sustains our metabolic activity in the middle. So this view is basically described in the book that was also recently mentioned on the thermodynamic foundations of the Earth system, and that I think that actually the person who originally initiated this workshop, and Vinod Gaur, probably was motivated to contact me with, based on that book. Anyway, so what we are having is, so we have conversions of energy. This is sort of reduced, simplified diagram. So we have energy conversions from radiation to heat to motion, chemistry. Life uses a shortcut, and we have humans, and we have planetary effects that are these red arrows. And what I want to, or where thermodynamics comes in, is that it's not just energy conversions that we have, but especially in this first part, I will show you some examples that it seems that at least in the climate system, processes evolve to their thermodynamic limit. And so because it evolves to the limit, they can actually become predictable by really simple models that can be used to quantify sort of basic patterns of energy balance partitioning and also climate sensitivity. But then we can think of life actually being able to draw energy here from the shortcut and alter the system to even alter these limits to generate more power. So what I'm going to talk about in the following slides is that I will give you a little bit of an introduction to thermodynamics, and an introduction that is very basic. You know, when I studied physics and I got a textbook on thermodynamics, usually, you know, on like page 10 or 12, you know, there were lots of differentials. And this is not what I want to get at all. I want to be quite general because I think it's actually something that you notice in everyday's life, thermodynamics and the laws of thermodynamics. So I really want to have their more accessible version. And we talk about some of the basics and hint at what are the important components. Then I want to briefly show some application to climate, to geochemistry and life, and last to the humans, and then just summarize this outlook and provide an outlook. So when I talk about thermodynamics in everyday life, for me a good example is a cup of hot coffee. When I start my day in the office, I grab a cup of hot coffee, and then we pretty much know what's going to happen. With time, the cup of coffee is going to cool down. Or actually, more precisely, it cools down and the room may get a little warmer because there's energy conservation, so energy is conserved, so the total energy needs to be the same. But energy conservation does not tell you anything about that the cup is going to get colder with time. Yeah, I mean, this is something else. And this is actually a reflection of what is known as the second law of thermodynamics, that actually energy wants to distribute. It wants to deplete gradients. It wants to deplete differences between the hot coffee and the cold room. Or more specifically, it's you know, what's in physics is called it's increasing the entropy of the system. So you actually increase, so you can only increase the entropy. Now, when we deal with Earth system processes, we don't actually deal with cups of coffee that get cold, but we sort of, and where things get degraded and we end up with cold coffee. Cold coffee is not quite the right picture for the Earth, which is reflective of equilibrium thermodynamics. But actually we deal more like with a pot of hot water that's on a stovetop and it is continuously being heated from below, that cools at the top, you know, evaporates and makes the kitchen warmer and more foggy. And where inside the pot you have work being performed in terms of the boiling motion that you have inside the pot. Yeah? And that's more of the picture of what happens in the Earth system. Basically, solar radiation is your heat source or your energy source. You have various processes in the Earth system that perform work, and then the planet cools by emitting long-wave radiation to space. Now, if you want to describe such systems, you need to think of fluxes. You need to think of rates. And so I want to briefly show you how one can actually describe the laws of thermodynamics in form of this non-equilibrium system. So on the one hand side, the first law in energy conservation is reflected in what's called an energy budget. So you balance the change of energy in the system with what comes in, what goes out, or what is being converted into another form. So far, so good. And then if you want to apply the second law of thermodynamics, this is something where I feel like I really missed this in my physics education. I mean, I might have slept or, you know, I don't know. At least I only recently, or no, not recently, but I learned this after my PhD, is that there is actually something that's called an entropy budget. So in other words, when you deal with a non-equilibrium system, where there's a flux going through the system, you need to have a budget of entropy. So you have here is the change of entropy of the system with time, and you have fluxes of entropy. So this is when you add heat at a high temperature, for instance, you add heat with relatively low entropy. When you remove heat at a cold temperature, you remove entropy from the system at a relatively high entropy. And then what the second law of thermodynamics says, that is whatever happens inside my system can only increase the entropy. It can only produce entropy. So this sigma here can only be greater or equal to 0. And those processes that produce entropy, they're called dissipative processes, and they always act to increase the entropy. So now when we talk about entropy and want to apply it to the Earth system, we actually need to recognize that there are different forms of entropy. And this is what I want to show you on this slide. So entropy, at the one hand side, measures actually, or it's well defined in statistical physics. You have a microscopic world where energy is quantized. It's at the scale of atoms, molecules, electrons, and where light is being quantized into so-called photons. And this is shown here on the left. So you have photons, carriers of electromagnetic energy. You have electrons that orbit around nuclei. And you have molecules that have certain kinetic energy. They bounce, they vibrate, they rotate, and distribute energy in those modes. And then the work that was done by Ludwig Boltzmann, actually he introduced that in the late 19th century, and then Max Planck picked it up for radiation around 1900, is that actually if you want to infer macroscopic properties like fluxes of radiation or temperature or some macroscopic properties like, go to the scale of solids, liquids, and gases, then actually you can do a scaling. You can assume the maximum entropy, so the most probable distribution of energy at the microscopic scale, and obtain certain characteristic relationships. For example, you can infer the spectrum of radiation of a so-called black body, and this is reflective of maximum entropy associated with radiation. And you have that black bodies that have a higher emitting temperatures have lower entropy than the radiation that is emitted by a colder body. This is what I show here in the blue. Then you have different molar entropies, so associated with electrons orbiting the nucleus. So, for example, typically molecules have higher entropy than atoms because they share orbits, and so the electrons have more states over which they can distribute the energy. And then the last one is thermal entropy, which is related to the energy stored in the different motions of molecules. And so why this is important is that actually you have entropy associated with radiation, so with radiative processes. You have entropy associated with chemical processes and phase transitions, and you have entropy associated with temperature and pressure, sort of what is typically known as classical thermodynamics. Now, if we want to put entropy in the second law, and now back to the planetary context, we can sort of simply say this is the journey of energy from the sun to space, or to Earth, and then to space, following the second law of thermodynamics, where we have a very hot sun inside. Then inside the sun you have convection, bringing the energy released from nuclear fusion inside the sun to the surface. The sun emits radiation at a high temperature, and then this radiation travels through space unaltered, hits the Earth. It's being absorbed, some of it is being absorbed, brings it mostly at the surface, but it's already much colder temperature at the surface. And then you have some more energy transfers from the surface into the atmosphere, and finally the atmosphere radiates it with the so-called radiative temperature to space. And so the radiation that is emitted from the Earth actually has a much higher entropy than the solar radiation that is being received by the Earth. And this difference in entropy exchange allows for a lot of entropy production inside the system, and it allows systems to perform work and create dynamics such as driving the atmospheric circulation. Now, another really important aspect about thermodynamics is that it sets limits to energy conversions. And this is quite well known. Typically, or you can illustrate this in using a power plant as an example, where you have the addition of heat to the power plant by the combustion of fuels. So you add heat at a high temperature. The chimneys, the cooling towers, they remove heat at a low temperature. And some of this heat from the combustion is converted or performs work and creates free energy. So energy that is able to perform work, just like, for example, electric energy can perform work, drive motors, drive heating or air conditioning, or so on. And one can very simply use the first and second law of thermodynamics, combine them to derive a limit, which is known as the Carnot limit, that describes how much of the heat you can maximally convert into work. That's a very well-known limit, and this limit, of course, also applies to the Earth system. So we can apply it to the Earth and see how much work can be performed, and this is actually what we want to do in the next couple of slides. So perhaps just one more point about energy conversions and generating free energy. So this conversion of heat, like in a power plant, this only applies to the lower part here of this diagram. This is sort of the difference in temperature between the surface and the radiative temperature. This is a one where you can drive a heat engine, and this is sort of what the climate system uses to generate free energy. These are heat engines, and I used the picture here of a hurricane to illustrate, this is physical energy generation. Then there are other mechanisms to use the low entropy of solar radiation, but you can't use it by heat engines, but you can use it by photochemistry, like, for example, that plants use, or you can use photoelectric effect from photovoltaic, where you directly convert the incoming sunlight into free energy or electric energy before it's being converted into heat. And that's what I show you here, is the conversion back into heat. So we will see those three pictures again throughout the remaining parts of the lecture. I first want to go to physical energy conversion, so like a hurricane, and describe the application of heat engines to the climate system. Now, I show this hurricane because actually that's the application of heat engines to the climate system is also not new. That has been done for quite some time. For example, Kerry Manuel from the MIT applied it to hurricanes to infer the maximum strength of hurricanes, and it actually worked quite well. It's quite impressive work from the late 1990s. So what we are going to do here is not to focus on hurricanes, but on climate in general. And as I described earlier, so basically, you have sunlight coming in, some of it being absorbed at the surface, heating the surface, creating some surface temperature at the surface. Then we have an exchange, emission of radiation from the surface. Some of it is being absorbed in the atmosphere, and then it's being radiated to space or back to the surface. And then we have here a heat engine that is being driven by this temperature difference between the surface and the atmosphere. And here I use this radiative temperature that I mentioned before, which is the temperature at which the radiation emitted to space has the highest entropy, so it's like an upper bound. And so this heat engine then derives work, which can be used to maintain motion. And motion then actually sustains these turbulent heat fluxes here at the surface that again drives the atmospheric heat engine. And so we can apply the Carnot limit to this that we have seen earlier. So the power that can be derived is proportional to this flux here, but also the temperature difference between those two reservoirs. Now, when we apply this to the Earth system context, one aspect that we need to account for is that temperature difference here is not a fixed property of the system, but it actually depends quite strongly on this heat flux. So what we have is actually that the more convection you have, the more motion you have in the system, the more efficiently the surface actually cools, reducing the surface temperature. And so this term here becomes smaller as this term here becomes larger. And I just sketched this here. So the temperature goes down with increasing flux, and that actually sets a limit to the power that can be generated. And I refer to this as the maximum power limit. Now, when we evaluate this maximum power limit, we can use this maximum power limit, and we get an optimum flux here that's driving this heat engine. These associated with motion in meteorology, these are called the sensible and latent heat flux. There are two components, one related to dry processes and the other one to evaporation. And we can evaluate this against data sets of observations, or not quite observations, I mean, they're here from a so-called reanalysis product. So the dots here show different grid cells and their climatological mean partitioning between the incoming, the absorbed solar radiation here on the x-axis and the turbulent fluxes here on the y-axis. And what you can see is here is this cloud. So you can see here the polar regions, temperate regions, subtropical and tropical regions. And what's shown here is the 1 to 2 line, because the prediction of this maximum power limit in a very simple parameterization with some simplifications actually predicts that's only half, or just half of the solar radiation that is being absorbed. And you can see that the order of magnitude actually fits quite well. There's some deviations from it, and there's probably something to learn from these deviations. But as a first order guess, it's actually a pretty good assumption. And what it actually then also implies is that the Carnot limit is not just a hypothetical limit, but it seems like that the atmosphere actually really operates at that limit. So this is work that actually was done, that we've done 5 years ago. Time passes quickly. And so more recently, we looked at diurnal variations and directly looking at observations. So these here are 4 examples of measurement stations spanning from Alaska, that's the tundra, to a grassland near Berlin in Germany, to a pine forest in Israel, and to a rainforest in Brazil. And what we show here is the observed turbulent fluxes here in these black circles, and what's predicted for maximum power here is the blue dashed line. And you can see that the agreement is actually quite remarkable. Yeah? And it's a slightly different limit here that I show you up here. It's a slightly different expression. And the reason why it is slightly different is because on the diurnal scale, we also have to deal with heat storage changes in the system. And heat storage changes represent a change in entropy that we need to account for when we derive a thermodynamic limit. And so this is a slightly different thermodynamic limit that I'm using here. So we learned actually something from that. But again, you know, thermodynamics seems to be able to do very good predictions of this energy balance partitioning at the surface. And actually, one of the reviewers of the manuscript actually said, well, this is probably better than GCMs. But this is another sort of point to be tested. Well, one can use this approach also to learn something about climate sensitivity. So how does climate change when we hit global warming, when the surface temperatures get stronger, or better to say, when the greenhouse effect increases in its intensity? And one prediction that we evaluated is how the hydrologic cycle changes with global warming. And for that, well, we make an assumption here, or we use a steady state assumption. So that means that the amount of precipitation is equal to the amount of evaporation. And the rate of evaporation we can actually directly infer from our maximum power limit with some micrometeorological constants here that I don't want to go into detail. But so we have an analytical expression, and when we evaluate the sensitivity of this, so when we take the derivative of this to temperature, we actually find that we can predict the relative change of the hydrologic cycle in terms of precipitation actually fits very well to what GCMs predict as well. On the other hand, what we also find is that if we try to compensate the global warming by reducing solar radiation, it's something called geoengineering, where you try to inject aerosols into the atmosphere to dim the sun. We can actually show that there too, the GCMs and our simple estimate actually work and match very well here. So we can not just reproduce the main state of the system, but we can also capture the sensitivities to first order very well. And so to briefly summarize this is that, so we talked about the conversion of solar radiation to motion, so it's a physical conversion, and it seems like that motion operates near its thermodynamic limit. You can apply the same approach to large-scale motion where heat is transported from the tropics to the polar regions, and you can find that there this limit also works very well. And when you evaluate how much power is being generated, you get an estimate of about 1,000 terawatts, which actually agrees reasonably well with estimates that are based on observations. So the magnitude of the turbulent fluxes can be estimated with an extremely simple approach. You can do it really with paper and pencil. You don't need complex math for this. And one really important distinction to, say, typical thermodynamics is that you really need to take interactions into account, because the interaction of motion or of convection with surface temperature is so strong that it alters or that it leads to this maximum power limit. Okay, the next part I want to talk about briefly is about geochemistry, or how the Earth generates chemical free energy which allows it to maintain chemical reactions, chemical transformations, and in which, of course, life also plays a large role. And I'm going to hit you with a budget, and I'm going to go slowly through this. So it's trying to summarize different forms of disequilibria, so chemical disequilibria where reactions can take place, and the processes that generate it, and rates at which these disequilibria are being generated. So for instance, we have that solar radiation, the absorption of ultraviolet radiation results in photodissociation, and so the breakup of molecules in the stratosphere, creating stratospheric ozone. And so you create a disequilibrium in form of ozone versus oxygen, and you also create some OH radicals out of water. And there are some estimates back from the 80s, and I just give you here a number. This is an estimate which is for ozone, it's about 20 terawatt of chemical energy that is being generated. Terawatt is 10 to the 12. The reason why I give you the number is because then we can actually compare how important life is compared to other forms of chemical energy generation. Then we have hydrologic cycling, which produces chemical energy, for example, by lightning or by desalination and weathering. You can see that these are sort of in a similar order of magnitude. But then when we think about photosynthesis, generating a disequilibrium out of CO2 and water, it creates carbohydrates and oxygen. We find that the number is about 10 times higher. It's 220 terawatts. You can estimate this from the rates of photosynthesis and say, wow, this is certainly the major source for chemical conversions in the Earth system. You can also then look at human activity. For example, we take fossil fuels and atmospheric oxygen in combustion, and there we use 18 terawatts from geologic reserves. So you can see that this order of magnitude is actually quite similar to these abiotic rates. And you can see that human activity is actually quite a significant term in consuming geochemical energy. Okay, so now I want to go a little bit into photosynthesis and ask, can we apply thermodynamic limits also to photosynthesis, right? So first I want to briefly talk about the mechanism. So usually what happens in creating chemical energy from sunlight is through two processes called photoionization or photodissociation, which is actually quite destructive. It really breaks up molecular bonds. It's almost like a sledgehammer that hammers on the oxygen molecule, breaks it up, then ozone forms, and then again ultraviolet radiation destroys the ozone molecule. So it's actually, well, it leads to chemical transformations, but it's really more of a radiative process. Now what photosynthesis actually mastered is the art of changing or to actually separate charge from the, to perform charge separation on the hydrogen atom without destroying molecules, but rather to do it in a sophisticated step or different steps to use 8 photons at least of visible light to split up water and to split the hydrogen into the proton and the electron. And then the proton and the electron then are further used to actually create ATP and then later on carbohydrates. And then when you look at photosynthesis, so you need 8 to 10 photons of about 1.8 electron volt of energy to fix one molecule of CO2. Then you can calculate how much energy this involves. And when you then compare the energy in the photons to the energy that is stored in the sugar, you come up with an efficiency of about 34%, which actually sounds, well, that's a decent efficiency. That's actually quite large. Well, actually, photosynthesis can only use half the sunlight because it can't use the green. This is why we see the leaves as green, because that's the reflected light. So that drops the 34% to only 17%. But when we look at observations, we actually find that the observed efficiency of photosynthesis is less than 3%. So, well, it seems, well, thermodynamics is not what the limiting factor is, at least not in the form of converting radiation into chemical free energy. So it operates well below this thermodynamic limit of energy conversion. Now you can look at patterns of productivity to see what the main limitations actually are. So this is here a map of net productivity. So that means it's photosynthesis minus what is being respired by the biosphere. It's combining estimates from satellites for ocean and land productivity from NASA, from a satellite called MODIS, for 4 years in the early 2000s. And it shows the productivity not in form of how much carbon is being taken up, but actually I converted it into units of watts per square meter. So one can see that it's actually not that much. It's about sort of 1 watt per square meter at most. And you see what the limits are. Actually, you can see that on land, there's no productivity in the deserts. And over the ocean, you see that there is actually no productivity in the subtropical oceans. And it is actually well known that is because there is a lack of mixing. You need the mixing to bring the nutrients back to the surface. And that's actually what the limiting factor is for the marine productivity. And so these two factors, water and mixing, are of course processes that are related to motion or to physical processes in the climate system. So one can say, well, perhaps it's not a direct thermodynamic limit on photosynthesis, but rather more of a transport limitation that is due to thermodynamic limits that constrain motion in the Earth system. In any case, when you integrate this, then you get about these 220 terawatts for photosynthesis. And so to sum up this part on geochemistry, well, I mean, first, chemical free energy is generated either by absorption of sunlight in photochemistry or indirectly by motion. For example, with a water cycle, also interior processes can generate chemical energy through motion. And when you estimate these rates, they are typically quite a bit smaller to what life is actually producing. So life is a dominating process. But it is not a process that seems to be close to its thermodynamic limit, but it's actually well below the thermodynamic limit, and that's probably because of physical limitations that may well be thermodynamically limited. So it's probably an indirect limitation. In terms of feedbacks, there, of course, you have well-known feedbacks of life on the planetary budget, because you, over the evolution of the Earth, life has actually substantially altered the atmospheric composition. It created a noxic atmosphere, and it removed much of the greenhouse gases that were presumably present in the original atmosphere. So it's changing the atmospheric composition, and by that it changes the radiative properties of the atmosphere that are at the very top of this energy conversion scheme for these physical energy conversions. So one may think that actually these geochemical effects of life may actually feed back to, and may actually enhance and even may maximize productivity, given that motion and mixing and transport are the limiting factors in the system. This is a hypothesis. It would need to be tested to see if this is actually, in fact, really playing out. Now, the last part I want to go into is human activity. And I think a nice way to show how much we have transformed the planet is this satellite image from NASA, where we see lights. So it's satellite images from the nighttime, and you see all the major cities here. You know, this is somewhere where I come from. This is the US. India is down here, and here's Japan, China, and you can see sort of that, you know, Europe and the US, they consume a lot more energy because they're a lot lighter than, you know, some parts of the tropics, where you don't really see much of Africa or Brazil, or central Brazil. Now, so when we think about human activity and thermodynamics, actually we are very closely related to energy, because what sustains us in terms of food is actually energy. And you know, typically we refer to this energy in form of calories. And you know, when you think of a dietary requirement of 2,000 kilocalories per day, for instance, that actually translates into an energy consumption rate of about 100 watts. So while we are sitting all here, or standing in this room, you know, each of us produces a certain amount, sort of around in the order of 100 watts of energy, and converting it into heat and heating the room. So this is energy that, of course, comes from the biosphere, right? I mean, we take this in terms of food production from the energy that is being generated by photosynthesis. Well, we also use a lot of energy. We actually use more energy in our industrial activity. And this is here a diagram that's going to show you that actually the gross domestic product as an indicator for economic activity is really well correlated with the amount of energy that is being consumed. So this is here for some countries, and sorry, I think India, I mean, I'm sure India is some of these dots, but I didn't label all the countries that did the dots because it's too full. But the point really is to show that this is very much correlated. These are logarithmic axes, but when you sort of make a best fit here, then you actually see that there is about 3,300 watts per person consumed in primary energy consumption. So you can see it's far more than what we use in terms of food. And you can even translate this into a rate, it's like an exchange rate, how many dollars per watt you produce in terms of economic activity, which doesn't mean you should start wasting energy and think that you become more economically productive, of course. But I hope this illustrates the point that, you know, human systems are very much dependent on energy. So when you integrate these numbers, you actually get that the food that we take up actually appropriates about 8 terawatts from the photosynthesis of agricultural lands. And the 8 terawatts is already, you know, a good number that compares to the overall 220 terawatts that are being generated by photosynthesis at the planetary level. But then our socioeconomic activity based on fossil fuels consumes quite a bit more energy that outnumbers this one by more than a factor of 2. And so my point here is that these rates of energy consumption are really in a similar magnitude as Earth system processes. Yeah? And I think if you follow this discussion about calling the current geologic era the Anthropocene, sort of a new era, then you can say, yeah, I mean, these are the numbers that support this, right? I mean, we are really a force that really alters the dynamics, the energy conversions of the planetary system. We also have effects of the Earth system, right? We also have feedback or effects and consequences. So, for example, by doing agriculture and converting natural lands into agriculture, we actually reduce the natural biosphere. The natural biosphere gets less of the cake that photosynthesis generates because we humans take part of this cake. And likewise, the consumption of fossil fuels that were locked away in some geologic stores alters the radiative properties of the atmosphere by enhancing the greenhouse effect due to CO2, right? So we can think of these as being also altering the dynamics of the system. Now, when we think about the future now, we need to get away from fossil fuels. One way is it's not sustainable, it's causing global warming, but it's not sustainable because it's a reserve, and we need to actually get into energy, we need to get energy from a sustainable source. So one is, you can think of renewable energy, right? I mean, this is ultimately a sustainable energy source. And I want to briefly show and put these numbers into a diagram that shows different forms of renewable energy, just a subset of them, but to show you one point, and that is here. So here we have the Earth system process. So we start with incoming solar radiation. It generates heating differences by absorption, and that drives atmospheric motion. It's like a little engine here, and then the atmosphere, as it moves over the ocean, generates waves. So we have ocean waves. And then ocean waves actually drive the wind-driven oceanic circulation. And when you take this picture from before, so you start with 175,000 terawatt of energy that we get from the sun, then the radiative differences that cause large-scale motion are only 49,000 terawatts. It's due to reflection and also the difference in heating. Then that's being converted into about these 1,000 terawatts associated with a large-scale atmospheric circulation. Only a small fraction generates ocean waves, and even less generates ocean currents, or wind-driven ocean currents. Now you can link these different conversion rates to different forms of renewable energy. This one here can be used as solar power. This one here is wind power. This would be something called wave power. This one here is related to powers that can be drawn from ocean currents. But what you see is that by far the largest source is actually solar power, right? Because every other source is already a converted form of energy. And so the more you convert energy, the more you lose, and the smaller your potential of generating some renewable energy. Now, humans have already actually developed technology that can exploit some of that renewable energy, in particular photovoltaics. And I think why photovoltaics is so significant is that when you look at its efficiency. So with plants we've seen, the efficiency is less than 3%. But when you take now current industrial grade photovoltaic cells, they already have efficiencies of 20% in using solar radiation, doing the work of charge separation and creating electric energy. The maximum efficiency that has been reached so far is somewhere in the upper 40s. And theoretically, you can go up to 70 or even 90%. So I think what it actually shows is that human technology can actually be better than the natural processes in generating free energy. And so when I bring this back to this diagram from the beginning, so we had sort of the physical climate system generating renewable energy from the climate system is down here, spanning this temperature difference. This is what's driving those conversion processes. Plants tap into this part. They don't use the heat at the surface, but they use solar radiation before it's turned into heat. And photovoltaic can actually add here even more. And so when you bring this picture now to sort of a broader scale of planetary evolution, you can think of these different forms of energy generation, and you can associate them with different types of planets. So this is what I'm showing you here. So you can think of a planet like Mercury. When you think of Mercury, it's actually quite a boring planet because it's a flying piece of rock. There's no atmosphere, and so it doesn't generate free energy. It absorbs radiation and emits radiation, and that's pretty much all there is in terms of the dynamics of that planet. Then you can think of Venus or Mars. Those are planets that have an atmosphere. So they can convert energy. They can drive atmospheric circulation. So they have some abiotic forms of renewable energy, but most probably no life and no sort of sophisticated technology. Now, when you think about these types 3 and 4, like early Earth or current Earth, we actually have life forming another mechanism to generate free energy. And when we extrapolate into the future, we can think about another type of planet where actually an advanced civilization created technology to evolve even, or to generate even more free energy to drive planetary dynamics. And so with this, actually, I think this is an outlook for a relatively more positive future than when you think of all the headlines with global warming that looked sometimes really grim. So I think that actually one can get into a trajectory where one gets into an even more active planet due to human technology such as photovoltaics. So now I want to sum this up. I noticed that I actually, as usual, I spoke much longer than I wanted. So I talked about the thermodynamics of planet Earth. And I think the critical additions to the thermodynamics is that there is entropy of radiation, that we need an entropy budget because it is a non-equilibrium system. We talked about thermodynamic limits that set speed limits on the conversions. And we have these sequences of conversion of energy from one form into another. Then I showed some applications to the atmosphere where motion operates presumably at its thermodynamic limit. So it's a sign that systems evolve to their limit. Then we talked about geochemistry where life is a major producer of chemical energy, and that doesn't maximize power, but it's probably because the physical environment constrains it so that it can't reach its limit. And so it may nevertheless maximize it because it changes the radiative conditions on the planet. And last but not least, I talked about the anthroposphere and that humans actually are a major consumer of free energy on the planet, comparable to other Earth system processes, but that we actually have the chance to increase free energy generation by the planet by using technologies such as photovoltaics. And with this, I want to stop and thank you for your attention.